Howdy, hi, AP Calculus AB. It is great to have you all back for our second targeted review. Um, this review is one I find my students are generally the most successful on. This is our rates in accumulation. Typically, this type of free response presents itself by giving both a rate in and a rate out in terms of two different equations on a free response question. Sometimes it can be just a single rate and they'll add the other rate later. Sometimes it'll be an equation that's a rate in and a table that's a rate out, but either way they function about the same. Very, very common to see. I would bet pretty good money that somewhere along the line you're going to see a graph of f prime. We saw that for our first targeted review, and you're going to see a problem with a rate, usually comparing a rate in and a rate out. It'd be a weird year if you didn't have both of those. So these first two videos, make sure you're good with them. All right, now this question that we're going to practice today is only one question, right? It's 2017 question 2, so it's fairly recent. However, I did, much like last class, add a couple extra parts on here just so we could see all the different varieties we might be asked on this problem. So what's happening? Well, a grocery store opens, has 50 pounds of bananas on a display table. No idea if that's accurate or not, but I think AP tries to be pretty accurate with their scenarios, so let's assume an average table in a grocery store is 50 pounds. Maybe next time you go shopping, you can check it. Who knows? Customers are removing bananas from the display table at a rate modeled by 10 plus blah, blah, blah from 0 to 12. Where f of t is measured in pounds per hour, t is the number of hours after the store opened. So at, let's say, 3 hours, that'll be the rate that customers are removing bananas 3 hours after the store is opened. After the store has been open for 3 hours, store employees start to add bananas to the display table at this rate. It makes sense. No reason to add bananas if only one has been taken off. So they start looking after 3 hours that the store has been opened up till 12. That's when they both close, and we should be good to go. Very first thing I'm going to do on this is not even read part A. I see two equations. I see calculator active. The first thing I'm going to do is put this into my calculator. I'll demo both the 84 and the Inspire. The 84, though, I already put these into my calculator. I am, of course, checking to make sure that I am in radian mode. Calculus is rad. Don't confuse that with the weird degrees that physics uses. And I'll do the same thing here. I haven't put it into my calculator yet. I like this button just to switch back and forth. And then I think I'll need to do something like this. There we go. Notice that this is called f1 of x and this is t. One of the most common mistakes I see people make is they use the variable t and then nothing appears on their screen, and that would be not good. So 10 plus 0.8x. And then I always like to put a times in between if there's a new function going on. Sometimes your calculator gets a little bit weird if there isn't something in between sign. And then don't forget that you have a fraction button here. You, of course, can do division too, but might as well use the fractions because it's there. Just a fancy form of division, right? X cubed over 100. And then we'll go down to our second one. And the second one is this guy down here. 3 plus 2.4 times the natural log of x squared plus 2x. Make sure your plus 2x doesn't end up here. That's no good. And you'll get the wrong answer. And I think we should be good there. Nice. We're only looking between 0 and 12, so I might as well change my window a little bit. Menu. And honestly, the first thing I should probably do just to make sure settings aren't weird is go menu, window, and then standard, which is 5. Nothing changes here. But if I do that on my 84, let's see, if I go to graph here, you'll notice that my window's weird and it's graphing kind of slowly. If I want to stop that, hit the on button. The on button will stop your graph if you realize that you're like, oh, didn't like something, need to change something, let's change the window. You might as well change the window. Don't waste the time, have it graph, and then have to change the window and have it graph again. So I'm going to do window, nope, I'm going to do zoom, and then standard, which is 6 on this one. And then we'll get something a little better. Okay, changing the window here, we said we only want to go between 0 and 12. Paranoid old me, I like to go one more in each direction. So -1, I use tab to move down. Go -1 to 13. Hit enter. That's a little better. It might be useful, too, to see where these two graphs cross or intersect at some point. So let's go a little bit higher up. Do we get any clues about how high up we're going to go? Not really. Yeah, I think we're just kind of eyeballing it here. So let's go ahead and just go to Window Settings. And maybe the negatives don't seem to really matter. But yeah, maybe we could go through and look at, let's go like -5 to 50. Maybe that'll be okay. And then just hit enter. Ah, it's way too much. Oof. All right, how about -5 to 25? Sounds good. And do you have to do this? No, I just like getting a good little picture of what's going on here. So -5 to 20. There we go. That's looking pretty decent, I think. Alrighty. Nifty. And then we can do the same thing on this guy too. So window, we went -1 to 13. Scaling can be by ones, that's fine. We want -5 to, what did I say, 20? There we go. And we can scale it automatically, or you can be awesome and say, I want to scale by 5s or something, whatever sounds good to you. And there we go. Hopefully it looks pretty similar. I think it does, though. Nice. All right. We have this going. Give me that other natural log graph. Perfect. Let's get started, shall we? How many pounds of bananas are removed from the display table during the first 2 hours the store is open? Well, the one thing we should probably identify that I didn't ahead of time, and I usually do, is which equation is the rate in, which equation is the rate out. Well, it's interesting because the first equation they give you is actually the rate out, right? It's the rate the customers are removing bananas versus our other equation is the rate in. If we want to know how many pounds are removed, the rate in is not relevant. It doesn't matter how many are added. We just care about the removal, which is our function up above. The one thing we don't want to do here, though, is just find f of 2. There's two reasons we don't want to do that. First, this is a calculus class, and if you just substitute in a value, you have not done calculus. Calculus is either an integral, a derivative, a limit, or interpreting something in a calculus sense. That one's a little bit more vague, but we'll talk about that as we go down. So it's definitely not going to be f of 2. The other reason I know it's not f of 2 is because they tell us that f is measured in pounds per hour, and we want to know how many pounds. So if we think about this, and I'll just kind of jot this down over here, f of t is in pounds per hour. I always like to just see this hierarchy. That means f prime of t is going to be, I don't know why I'm writing out pounds, I'm pretty sure there's a shortcut for that, pounds per hour, and the antiderivative, maybe I'll do capital F of t, would just be pounds. So if I have f of t and I want to get up to capital F of t, we need to do the antiderivative. So how many pounds are right? All right, so to go from lowercase f of t to capital F of t, we need an integral. Remember, this integral is a fancy s. It means we're going to sum up all the bananas removed, starting at 0, ending at 2, using f of t dt. Now, you're trying to save time here. So I saw some of my students on my latest test go, okay, we're doing that, which means we're doing the integral of, and then they rewrote this whole equation. You don't need to rewrite that whole equation. In fact, I would suggest you don't. The only work you need to show on here is that you're integrating from 0 to 2 of f of t. Right? They named the equation f of t. They know what f of t means. This is the only math we need. So let's go through and find that integral. Okay, I'm going to go back to my home screen, and we're going to do some calculus. Menu, calculus, integral, and we're going from 0 to 2. My rate in equation is labeled as f1 of x. I'm sorry, rate out equation is f1 of x, so I'm not going to retype the equation. I'm just going to type f1 of x, and then dx. And then on these, you really probably want to start getting in the habit, if you're on the Inspire, doing control and then approximately to get the decimal. However, in this case, I imagine I'm just going to get a decimal anyways. Also, we want to make sure we go enough decimal places. Some of your calculators will only go to 2 decimal places. We want to show more. Currently, mine is showing 4 past the decimal. That's known as a float of 4. So if you wanted to change your calculator so it would show the right number of decimals every time, you can go to your home screen, go to settings, and then document settings. And it says float 6. What if I floated more? And I guess I said float 4. Sorry, float 6. Let's try a float 8 and see the difference. Okay, I'm going to go back here again. I'm now on float 8. Look at that. So the float is the number of digits you'll see, And so I usually set float 4 because, I'm sorry, I keep saying float 4, float 6, just because that's a pretty good way to get at least 3 decimals, but I'll keep mine at float 8 for now. 1, 2, 3, 4, 5, 6, 7, 8. And that way you can at least ensure you're seeing all the digits, right? You need to go at least 3 digits past the decimal. Now, if you didn't have that, let's say you just had this number up here, your calculator doesn't just stop. If you copy it by hitting enter, it will show you all the digits it can, right? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. This is a float 14 right here. But it's probably a good idea to set it to float at least 6 or more digits so that you don't accidentally only write in the first 2. So 20.051. And how many pounds? So that's going to be pounds. That's it. That's all the work you need to show, right? Nothing bad at all. If you wanted to do that on the 84, very similar idea. We would have to quit. We'd go math, and then 8 is the derivative. So hopefully you're used to just doing math 8 by now. And then ddx. What equation? Well, my equation is hidden in y1, or that's where I typed it in. Oh, I'm doing the derivative. Oh, man. Doing really well here. Math 9. There we go. From 0 to 2, the equation is still in y1, and with respect to x, there we go. Same answer right here. The 84 will always show you as many digits as it can. If you copy this down, it shows you the same thing. So, should be just fine there. All right, let's motor on through. The rest of these should go a little faster. What's the average rate that bananas are being removed from the display table? So again, we're talking about removal, so we're talking about f of t still. The average rate, well, here's what I see a lot of students do for this. They go, ooh, I know how to find the average rate of change. I'm going to do, let's see, over 12 hours, I'm going to do f of 12 minus f of 0 divided by 12 minus 0. And they're not wrong in that this is the way to find an average. But look at the units we're dealing with here. These units will be pounds per hour, and 12 minus 0, those are hours. So when we do the final math here, we're going to be in pounds per hour. And so this isn't the average rate that the bananas are being removed. This is, in one way to think about it, the average acceleration, or it's the average second derivative, right? It's this average down here. I want to find the average of f of t because f of t is the rate that's being removed. This is finding the average for f prime of t, and we can see that for our units here. So this is a way to find an average, but it's not the average that we want. And I understand that this does get a little bit tricky, so I'm going to try to phrase this down below so that you can see the two different ways we have to find an average. The second way we have to find an average I affectionately call the average value theorem, and that is when we do 1 divided by b minus a times the integral from a to b of the function for which you're trying to find the average. Now, what does this find in comparison to what's up here? Well, let's look at the units, right? F of t, we already know, is in pounds per hour. dt, that's a change in time. If you measure how much time changes, that's in hours. But then there's more units out front. If you look at the units out front, 1 doesn't have units, but 12 and 0 do. 12 and 0 are in hours. So what's going to happen here? Well, these hours will undo. When you do the antiderivative, you'll get capital F, which is in pounds. But then you're dividing by hours at the end, so our final units will be pounds per hour. So really, this kind of goes in a circle, this average value. It does the antiderivative, and then it kind of, air quotes, does the derivative, end air quotes. So this is the way you find the average of whatever function's inside. If it's f of t, then it finds the average of f of t. If it's capital F, it finds the average of capital F. This is what we want. We want to find the average rate. F of t is the rate. How do we do it? Oh yeah, we do the calculator. Right? So nothing bad at all. I'm just going to stick with the Inspire. You guys know how to do this on the 84 as well. It's going to be 1/12 times, and then the integral from 0 to 12 of that same function, f1 of x, 10.564 units pounds per hour. Great. That's it. That is the average rate bananas are being removed. So essentially, every hour you are losing 10.5 pounds of bananas. Find f prime of 7. Using correct units, explain the meaning of f prime of 7 in the context of the problem. All right, again, my students just had a practice AP exam last week, and I saw this so often. Just too much work. And it was very good of them, and honestly, many of them did it correctly, but so much work. They said, okay, f of t we know is 10 plus 0.8t times the sine of t cubed over 100. And they said, now to find f prime of 7, I know first I need to find f prime of t. 0, and then you have to use a product rule in here, and they found that, and then they found f prime of 7, which, if this was a non-calculator active problem, would be a great way to do it. But this is calculator active, and your calculator has a way to go from an equation to the derivative without this intermediate step. Why take the chance that you might screw up somewhere on the product rule or the chain rule when your calculator will do everything for you? You are not expected on a calculator active problem to show the derivative equation. In fact, I would do none of this, right? If we want to find f prime of 7, the expected way you do this is you do it on your calculator, right? So we have menu, calculus, derivative at a point, -2, yours is probably 1 if it's not a CAS calculator, variable x, value 7, enter, and we want to find the derivative of f1 of x. Don't forget the of x in here. If this isn't working for you, you can type out the entire function if you'd like, but this I think is much quicker. Enter. There we go. -8.119. What about those units? Well, we talked about units earlier, right? This is why I write it out. That way it's really easy to tack those units on at the end. It's pounds per hour per hour. Usually problems like this are worth 2 points, 1 point for the answer and 1 point for the interpretation with the units. So unfortunately, just putting the units here won't give you both points because we need to explain the meaning and context of the problem. What's the problem's context? Well, the problem's talking about bananas, so my answer better talk about bananas. Now, students really struggle with this pounds per hour. Although it is the acceleration, we really want to go back to what a derivative measures. This derivative is measuring how f is changing, right? F prime measures the rate of change of f. So I always start with f, right? We say f of t, the rate bananas are being removed is changing at t equals 7 by -8.119 pounds per hour. And that's it. We start, so our intro is what is the thing the derivative measures the rate of change of? We are measuring the rate of change of f, and we gave it context. And then the second half of the sentence is, how is that thing changing? Well, f is changing, a derivative measures the rate of change by this. Now, if you really want it to be bold and you're like, but changing, that's so vague, why couldn't I say decreasing? You could. So, alternatively, you could say decreasing at t equals 7 by positive 8.119 pounds per hour. And notice if you say decreasing, you need to put a positive rate because decreasing already implies a negative. If you put an extra negative and you decrease by a negative rate, now you're increasing again, and that's no good. So you could say this if that makes you feel happier, but changing is just the safer way, right? This is the rate of change, and that's it. That's all the work we need. All right. Evaluate the following integral, then interpret your answer in context of the problem. They wanted us to do g of t minus f of t. Okay, I can do that. So we have menu calculus integral from 0 to 12, and they wanted us to do f2 of x, that's where my g of t is hiding, minus f1 of x. There we go. dx. Perfect. 8.533. All right. What did we just find? Well, it looks like they're subtracting the two rates and then they're integrating the rates. So this has got to be an amount. This has got to be bananas, right? Or maybe pounds of bananas if you want. What if we broke this apart? What if we used our properties of integrals? Uh-oh, it's 3 to 12. Ha, drat. I went, messed it up, didn't I? Alrighty, easy enough to fix. We'll copy this down and we'll change this to become a 3. There we go, 20.423. Oof. Alrighty, second try. What if I broke this into smaller pieces? I said 3 to 12, g of t dt minus the integral 3 of 12, f of t dt. Well, if this is a rate in, wouldn't this be the total pounds added from 3 to 12? And then if we integrate the rate out, then this, of course, is going to be the total pounds removed from 3 to 12. Okay, so what did we find here? Well, if we just looked at the table from 3 to 12, then it's going to tell us the total number of pounds on the table almost. I can't say exactly, though, because we don't know how many pounds are on the table from 0 to 3, so maybe this is a better way to think about the displacement of the table, right? This is going to tell us from 3 to 12 how different the number of pounds of bananas are on the table from 3 to 12. So because we got a positive amount, what that's telling us is when the store closes at a time of 12, there are 20.423 more pounds of bananas on the table than there were at a time of 3. All right. Should have written that out. Either way, you got it. We're moving on. Part E. Write an equation to describe the total number of pounds of bananas on the display table at any time t such that t is between 3 and 12. All right, this one's going to be a little bit trickier, I think. Whenever we write a total amount, need to take into account 3 things. So we need to take into account the initial amount plus the amount added minus the amount removed. And notice these are all in amounts. So I don't want to be using g of t and f of t here because those are rates. We need amounts. Let's rock and roll. A of t equals, the initial amount was 50 pounds. They told us in the problem. How much is added from 3 to 12? Well, we know they start adding at 3. And if we want to figure out the number of pounds at any time t, we don't know when we're stopping, right? We're trying to determine the actual time, or we need t so that we can use the actual time. This is going to be g of t dt minus, and then this one's a little bit trickier here because people start removing the bananas at a time of 0. So even though it says between 3 and 12, we still need to sum up how many were moved at 0, right? 50 was at 0 as well. And so we need to account for that 0 there. This problem is pretty tricky, having 2 different starting times on this. And then I think we're almost set. One small mistake. You'll notice that if I wanted to find the time or the amount, the number of pounds of bananas on the table, let's say a time of 7, then I'd replace t with 7. But which t? There's so many t's in this problem. Well, I think I'd want to sum up the amount added from 3 to 7 and the amount removed from 0 to 7. But I don't want to replace these with 7. That would be really strange. G of 7, D7, right? F of 7, D7. And so to account for the fact that there's so many of the same variable, we use that dummy variable. And so we're actually going to call this G of x dx and F of x dx as well. And that way we don't get confused about what variable is what. G of x is just an equation. It's not changing. It's that same equation. How many pounds of bananas are on the display table at a time of 8? Well, that's easy. That's just a of 8. A of 8 is going to be 50 plus the integral from 3 to 8, g of x dx, minus the integral from 0 to 8, f of x dx. Okay. I would probably just go straight through to the answer here, but it is always important to show the setup and the answer. Just because you have a setup earlier doesn't mean you shouldn't show it again. The one thing we don't want to do is just say a of 8 equals an answer, because oftentimes points are given for the setup and for the answer, and if you don't show the setup, you won't get those points. They call this a bald answer if you just give an answer and don't explain how you got it. So let's go through and get this done. Looks like it's going to be 50 plus the integral. Start getting used to those shortcuts, right? From 3 to, not 12, 3 to 8 of f2 of x. Be careful about your order here. Dx, there we go, minus, nope, stop that. Forgot to go right, there we go. Minus, and then we have our integral, calculus, cool, from 0 to 8 for the amount removed, f1 of x, dx. That should be pretty good. And we find that we have a current amount of 23.347. 23.347 pounds of bananas currently on the table. So, I mean, if you started at 50 and now you're down to 23, I think that gives you a pretty good indication that people are removing bananas faster than can be added back on, right? We're like approximately 27 or so pounds of bananas down from where we started. Actually, relevant, is the number of pounds of bananas on the display table increasing or decreasing at a time of 5? Well, there are two ways to do this. I'll give you my favorite way. We know the equations that are in charge of increasing and decreasing, right? Increasing the bananas is g of t, decreasing them is f of t, the amount that they're removed. So I really like to just compare the rates at those two times, f of 5 and g of 5. Okay, so f of 5, g of 5 right here. So we have f1 of 5 and f2 of 5. 13,795, and I'll have to go back for the second one. My memory's not that good. And 11.532. Remember, these are both rates. This is our rate out, and this is the rate in. Probably a good idea to write that so you don't mix these up. Well, if the rate out is larger than the rate in, then what's happening at a time of 5? Oh, that's right. More bananas are being removed, which means the number of pounds of bananas on the table are decreasing. So we'd say number of pounds of bananas are decreasing because f of 5 is greater than g of 5, the end. Now, be careful because they will want to actually see these values. They want to make sure that you're not guessing at this. So I would heavily suggest that you actually state these values on your paper before stating this. I've had some students in the past who just do everything on their calculator and they just write the sentence. They exclude this at the top, and I would not suggest doing that. Explain that you know what you're actually talking about. Now, sometimes my students will say, well, wait, we didn't actually do calculus here. We just plugged in two numbers. True. Technically, because f and g are derivatives, and you're interpreting derivatives, you're interpreting calculus, but not everyone likes that, so I just wanted to give you a second way to think about this. And the second way is, if we wanted to find if the amount of something is increasing or decreasing, we would usually start with that equation, and we have that equation from earlier. This is just an alternate way to take a look at this. G of x dx minus the integral from 0 to t, I'll zoom in, sorry, f of x dx. This equation told us the amount of bananas. And whenever you want to find if an equation is increasing or decreasing, you need to look at the derivative. So let's take the derivative of this equation. A prime of t, 0, derivative of an integral. We use the second part of the fundamental theorem, that's g of t, derivative of an integral minus f of t. Here's my derivative. Then let's see what's happening at 5, right? This becomes g of 5 minus f of 5. And I think you can tell if you subtract these two, and I'll even do it on the calculator over here so I can be accurate. We're doing g of 2 minus, and I'm just going up and copying these. You can do this on the 84 as well. Negative 2.263. Okay. So then my sentence would have been pretty similar. The number of pounds of bananas are decreasing because a prime of 5 is less than 0, right? If a derivative of an equation is negative, then that function is decreasing. If the derivative is positive, the function is increasing. So two different ways to think about it. I'm more fond of the first way. I think it makes more logical sense to me, but some students like doing it the second way, and that's great. Both of those work. When is the pounds of bananas, when are the pounds of bananas at a maximum on the table over the interval from 3 to 8? Justify your answer. All right, well, I actually want to approach this from two ways because they said when is the pounds of bananas at a max, not what is the maximum pounds. So if you think about a candidates test, and I'm going to erase this shortly. This should probably be T, huh? Well, what are the steps to the candidates test? Well, you'd have to try 3. You'd have to try 8. You also have to find the critical points, yeah? And so critical points are found by taking the derivative, that's this guy, and setting the derivative equal to 0. So we might as well do that. We might as well take g of t minus f of t and set that equal to 0. G of t equals f of t. How do we solve? Well, we have two different equations here, right? This is my f2 of x, this is f1 of x. We can just graph each one and see where they intersect. So let's at least start with that. I think regardless of how you wanted to do this problem, you'd have to find the critical points required if you're finding maxes or mins. So I'm going to go ahead and do the same on mine. It looks like I can even change my window a little bit, right? So this is going a little bit too far. I'm going to change my window just to go between 3 and 8. So menu, window, window settings. We're going between 3 and I'm, again, always a little suspect, so I'm going to go between 2 and 9, just in case something happens really close to between 3 and 8, right? That's going to be too far over, I think. So it looks to me like there's only one critical point. Let's double check that. Menu, analyze graph. We're going to find the intersection, 6.4. And again, I don't trust that either, so I'm going to do plus. There we go. Look at all those extra decimals, right? I used the plus on top of it to see all the extra decimals. Very important there. And then I'm going to check the other one just to, again, to make sure. I mean, what if this was 7.995? They actually did that one year where they had you set your, or they said we're only looking between 0.12 to 1, and one critical point was like 0.121. It was right next to the window. So since then, I've always made my window go a little further. So let's check that one as well. Analyze graph, intersection. All right, 8.833. That's outside of what we're looking for. So if you want, you can actually click on it and hit delete. You're supposed to. I said go away. There we go. And so we just have this single, 6.396. All right, so t equals 6.396. Cool. Now, in this situation, you have two options. Option 1 is, I'm going to redraw this quickly. That was just ugly. There we go, 6.396, and the other one was 8. Option 1 is you can find the amount of bananas on the table at all three of these. I mean, you have the equation up here. You can use your calculator. It's not too bad. But option 2 is what I want to talk about today because there's only one critical point on this interval. And a lot of times, it's easier to just create a quick sign chart and write a sentence, 2 sentences in this case, to get your answer than actually finding the amounts, because they don't ask for the amount here. They just want the when. They just want the time. So if I can narrow it down between these three, we should be okay. So let's go ahead quickly and take a look at the derivative, right? This is our a prime of t, which is this guy up here. We're looking from 3 to 8. There's only one critical point that caused our derivative to be 0. Okay? And then we should probably try a couple values, right? So we should maybe try something between 3 and 6 and something between 6 and 8. We already tried something between 3 and 6. That was negative over here. We tried 5. Between 6 and 8, though, you could either do it on your calculator on this screen, or you can actually get the answer just by looking over here, right? We're doing F2 minus F1. We're doing G minus F. So G is below, and we subtracted a bigger function. So smaller minus bigger got us a negative answer. That was like a prime of 5. However, over here, notice G is above and F is below. So if I do something like, I don't know, let's say this is 10 over here minus whatever the y value is, like 6. 10 minus 6 is definitely positive. So we can see one is on top of the other. But again, if you don't believe me, we can jump back over here and we could just do something like G of x, which is F2 of, I don't know, let's do 7 here. Minus, and then F1 of 7, and we get something positive. All right, so that is definitely going to be positive. And if we fill in our sign chart here, I think we're going to actually be in a bit of trouble, which is unfortunate. So we decrease and then increase. So by looking at the sign chart, they're asking for when is the pounds of bananas at a maximum. Unfortunately, it looks like we are backwards here. I was hoping that this would be a max. This is a min. So if they asked when is the pounds of bananas at a minimum, we would have been golden. We could have said because 6.396 is a relative min and it's the only critical point, it's an absolute min. However, now I'm not sure if the pounds of bananas is at a max at 3 or 8. So we are actually going to go through and find each of these. Luckily, we already found 8 earlier, 23.347. 23.347. Get out of here, line. We do need to find these other two. So let's get to it. I'm going to go ahead and use my calculator to do the rest. We do need to use this equation multiple times. So we're going to just go up, and actually I might even be able to copy it, huh? There we go. Yeah, we'll copy this down, and then I think I can just change all of this. There's an extra comma there. There we go. So we wanted to go from 3 to 3, and be careful here because you don't get an answer of 0. You get that 0 people have added, but some people have taken away. 19.613. Okay. And then let's also find 6.396 just for fun. And a nice friendly reminder, if I want to use this 6.396, I really want to use the most accurate decimal as possible. So I'm going to store this really quickly. And the way we store is you hover your mouse over. You do that by running your finger over here. You hover your mouse over. You click one time. Once you've clicked once, Control Store, and then pick a letter. I'll use A. If you're on the 84, you can do that as well. Right? If I wanted to find my intersection point, we'll go from, what do we say, from 2 over to 9 this time, yeah? There's one graph. Then we'll need the other. We can see that nice intersection point. Lovely. So we'll do calculate the intersection. We want to bring our little blinky spider as close to the intersection as possible. We're on one of ours, hit enter. Now we're on the other equation, still pretty close to the intersection, hit enter. And it says, should we guess between those? Yes, please. And it gives us this intersection right here. Now to store this one, it's a little bit trickier. Currently, your calculator has already stored this in terms of x. So if I do second quit back to your home screen and type in x and hit enter, you'll see that intersection. But as soon as you do another calculation with your calculator, it will delete this intersection and replace it with the new calculation. So I want to store that long term. So to store it long term, it's already right here. So I'm just going to hit the store button. It's going to take the previous answer. So it does answer, store is the arrow. What do you want to store it as? I'll be consistent, alpha, A, and hit enter. And now whenever I type in A, I get that same point, and that won't delete. Same thing on the other calculator. If I type in A, it's bold, hit enter, and we'll get the full thing. If I hit enter on it, you'll see it has many more decimal places than it shows. Why did I do that? Well, now, when I find my total amount, I'm going to just use A. And this is going to let us be as accurate as possible instead of using a rounded value. And actually, we'll compare the two values in just a second too. 14.073. Let's see what would happen if I use 6.396. I'm just curious. We'll see if it's that different. 6.396, right? 6.396 and 6.396. Those are pretty darn similar, right? They don't actually start to change until, what is that, 6 places after the decimal down here. So that's so negligible, it wouldn't have made a difference. If you'd used this, you would have been fine. And if you don't have the time, yeah, use just out to 3 decimal places. But if you do have the time, please use the most accurate value as possible. All right, once we're here, we can tell that the time that the pounds of bananas is at a maximum is going to be at 8. And so we would probably write a quick sentence, or you could say time for the max. At this point, you want to jot down a couple tips, tricks, or techniques, whether they're with your calculator, whether they're with writing this full accumulation function using the initial, amount added, amount removed, talking about units, whatever sounds good, anything that's stuck out with you. And while you're doing that, I'll just do our quick conclusion for the day. For rates and accumulations, you're going to have to identify how much of something either entered or left during a specific time interval, and that's an amount. You'll be given a rate, which means you'll need to do an integral. You'll need to create a function, which is usually called the accumulation function. That's going to incorporate the initial value, the rate in, and the rate out. You're going to have to find the time your amount was at an absolute max or min, either the candidate's test, or if there's only one critical point, then you could use the lonely critical point theorem. You need to understand how the units change, right? I always just like to write out myself a little chart, not a bad thing. And you'll need to be able to find an average rate, right? Comparing the average value theorem to the average rate of change. Hopefully you found this helpful, and I'm excited to have you guys back for our next video next class.